So, good afternoon, everyone. Welcome to the sixth week of structure analysis course. This is a problem solving section wherein you will see how we will solve the problem related to the sub topics that are covered in the previous week. So, let me share my screen first. Yeah, I think the voice is audible to you all, and you are seeing my video. Okay, so let's get started. So, this is the sixth week for the structure analysis course which is provided by NPTEL. My name is Prana Mahajan. I am a PMRF scholar in IIT Madras in Structural Engineering Division, Department of Civil Engineering. So, previous week we have covered how to calculate the deflection of frames and beams using different methods. So previous week we have done the conjugate beam method and using virtual word method, which utilizes the concept of unit load method to determine the deflection of beams and frames at a particular point. Uh, Previous week, that is week four, what we have done the same thing, but we have utilized the movement area method to solve the problems. So if I recall what we have covered till date, so started with the equilibrium things, we have take a beam section or any frame section. We try to determine the reactions. So first of all, we have to started with different types of supports that are available with us, and we try to find out various reactions at different points of the beam element. And then if frame is there, though, then we have tried to find the reaction that frames also. Then we went to calculate the stability also. So depending upon the type of supports and type of loading acting on the member, so whether that beam or the frame is stable or not at that particular position. So we utilize the concepts and try to find out the stability and the determinacy of the structure. So after determining the reaction force at various points, so we have calculated the shear force and bending moment at each and every point and then drawn the shear force and bending moment diagram for the corresponding beam and frame or frame element. Next week, when we have moved to trusses, we call the trusses to be a two force member in which either the compressive force or tensile force is acting on the member. So we have seen that how to calculate these forces in the member. So we have utilized two concepts. One is method of joint, another is method of section. So in method of joint, we try to find out the forces at a particular joint and using the concept of equilibrium equations, that is a summation of forces either in horizontal direction or in vertical direction equal to zero, and moment at a particular point equal to zero. So these three equilibrium equations we use to calculate the unknown forces in a particular truss member. Then we also utilize the concept of method of section, wherein we will use a stud section and divide the truss into two parts, and unknown reactions are calculated for a particular joint, wherein we use maximum times we use the concept of summation of moment at a particular point equal to zero, by which two unknown forces that are there that will be eliminated out, and only one unknown force will be remaining that we can calculate the value based upon the type of section we have considered. In third week, we have calculated the deflection of trusses using the principle of virtual work. So what we have done in that, we have utilized the concept of unit load method. So what we have said in the principle of virtual work done, that the internal work done should be equal to the external work done. So when we have utilized that and put the external force applied on the member equal to 1, then we will get the formula for the deflection, whether it will be horizontal deflection or vertical deflection, that you can say it as PTL upon AE or N L upon AE that you have seen in the NPTEL videos. But if you see some books, you will find it to be as PKL upon AE, where P is the force and that particular member due to the external loads that are applied on the trusses. Okay, K is the force on that member due to the unit load applied at the point where deflection or horizontal for deflection or vertical deflection is required to be calculated. L is the length of the member and A is the axial rigidity of the corresponding member. So based upon that, this is what we have covered till date. Now, in the coming week, what we are going to study, or what we have, what you already have seen in the videos, is the influence line diagram. So where we generally use this influence line diagram, so we mostly utilize this concept in bridges, wherein a train is moving over a pier and a abutment. So corresponding UDL is moving over a certain length of the bridge. So how the reactions or the movements are developed at various points of the bridge, that is abutment and piers, based upon the kind of loading that is acted upon by the train members. So that is the influence load member. So now we are not concerned about the point load, that is a static load. Now we are concerned about the moving point load. So influence line diagram gives you, it gives you the reactions and moments due to moving load. Okay, so how you have done that? So some maybe you have seen the video also. So what we have done, suppose we have a beam element. Okay, so if we have this beam element, simply supported beam. Okay, so now you have a simply supported beam available with U, BC, and suppose the point load is currently at this position. So for this, take it as 1 kilonewton, and this distance is h. Okay, so what will be the corresponding reaction at that point? So the corresponding reaction at that at point B will be if this is h, this would be L minus h. Now now you will be able to calculate the reactions at various members when it is subjected to different kind of loading, that you need to calculate by your own. Okay, so it would be By will be L minus h upon L, and Cy will be h upon L. These will be the reactions when the unit load is between E and C. Now, what will happen if the load is between B and E? Okay, it means the load is now moved to a different position due to when it is moving from left to right. Okay, so suppose now the load has shifted to this position. Now this is your 1 kilonewton load, and this is your distance h, and this is your distance L minus h. Okay, so in this case, your By will be L minus h upon L, same. Cy will be L minus h minus L upon L. Now, here, what will happen if you want to calculate the shear at E? So, what will be the shear at E? So, use sign conventions that are provided with to you. So, suppose this is your By. So, at any particular section, your VC will be downwards, and you have an anti-clockwise moment here, that is ME. Okay, so your now your VE will be minus h upon L, and your ME will be h upon 2. Okay, Now, if your load is at a different position, let me add another slide. So now, if your load has different position, again, like you have earlier in if it is between E and C, what will happen to the shear force and bending moment at at point E? Okay, so suppose this is your E point, and your load is your load is at this position. So now, what will be your shear force at E? So now this time your shear force draw it no, draw your free body moment, free body diagram. So this will be your By. So this will be your Ve. This will be your Me. Okay. Now load is not in between. So this time your Ve will be L minus H upon L, and your Me will be L minus H upon 2. Okay. Now if you draw the influence line diagram, so now how you will draw? So suppose I am drawing the influence line diagram for By. So for By, say, see, at a particular point, it is coming out to be. So this is your point B, and it moves to this point. Okay. So this BC. So this is your ILD for By. How we have made this? We have seen in the previous two slides. See, By is L minus H upon L, Cy is H minus L H upon L. Okay, so put H is equal to 0 in By equal to L minus H upon L. If you put H is equal to 0, so it will be equal to 1. Now, when you put By equal to, if you put By equal to uh, L, so if your H is now L, so now this will be 0. Okay, so that's why it is varying from 1 to 0. So this is how you will calculate the ILD for By. Okay, now again make ILD for Cy. How you will make? You will utilize the concept of reaction force at Cy. So now at Cy, at H is equal to 0, the bending moment is 0. Oh, sorry, the reaction force at B is equal to 0. Okay, because you utilize the concept of Cy is equal to H upon L. Okay, at H is equal to 0, it is 0. At H is equal to L, it is 1. So this will be your ILD for Cy. Okay, now let's move to draw the ILD for uh, shear force at particular point. If we make shear force at that particular point, when the load is between B and E, you have VE as H minus H upon L. So it means it varies linearly till L by 2. And from this position, it becomes L minus H upon L. So it would be like this. So this is your ILD for shear force at point E. Okay, if you put the value as L is equal to L by 2, because point E as E is equal to L by 2 length. Okay, so if you substitute the value in VE, you will get the value as zero point 0.5. So here the value will be zero point 0.5. So here the value will be minus zero point 0.5. Now if you draw the ILD for what you say, bending moment for each for point E. Now what you will get? So I will make it here only. So suppose here it is the point E. So what you will get? See, okay. So here, if you put the value as L by 2 in E equation, in this equation, if you put the value as x is equal to L by 2, you will get the value as 1 by 4. Okay. So here, this ordinate is 1 by 4. So this is a B, E, C, E, and this will be your ILD for ME. So now what all of these diagram signifies to you? What these signifies that suppose due to this moving load, you are required to calculate the force at a particular point subjected to a unit reaction, suppose Vy. So if you multiply that force with that particular ordinate, you will get to know the value of reaction force at that particular point. Okay, so this is the main purpose for solving that. Now, if you want to consider another example, let me add another one. So suppose you are having a cantilever beam. Okay, so this is his point C, this is point B, and this is point A. And let this distance be B in between. Okay, so your load is moving from A to B, and suppose your load is in between A and C. So now how it will look? So this will be your AY. At B there is no support reaction, and this is your point load. Okay, so suppose it is at a distance of h from A. So your AY here will be 1, and your MA will be minus of x. Okay. Now the load has shifted to CB. Suppose now this is your load. So AY will remain the same, and your MA will also be same. But please see the value of H is changing. It is not remaining same at each and every point. Okay. So if you want to calculate the value of moment as and shear at point C, what will be that? So when the load is between A and C, it will be having like this. So suppose this is your point B, this is your point C, and I will make this as VC. So now why I am taking it as upward force? Because I am taking the section from the right. If I take from the section from the left, my VC will be in the downward direction. Okay. So in this case, your since there is no load, so VC will be 0 and MC will also be equal to 0. Now take another section when the load is between B and C. So this is your 1 kilonewton load, and this is your VC, and this would be your MC. Now in this case, your VC will be equal to 1 kilonewton, and your MC will be equal to minus of H minus B, because this whole distance is H. And if you subtract the B, so you will get only this distance. So what is this distance? This distance is H minus B. Okay. Now, if you want to calculate the value of means ILD for each and every component, so let's draw the ILD. So suppose this is our beam. So AY at both the points, it's one only. So AY will be constant. Okay. So this is our ILD for AY. Now, if you want to calculate the ILD for MA, so let me draw that. Since the value is coming out to be negative and it is minus h, so it will be linear only. Okay. So here it would be minus of L, minus L. This is your ILD for MA. Now want to draw ILD for VC. So this is your A, this is your C, this is your B. So between A and C, VC is 0. After that, it is 1. So the ILD will be like this. So this is your ILD for VC. Okay. Now, if you want to calculate the ILD for moment at C, so how it will look like? So again, between A and C, the value is 0, and from C to B, it will be this one. Okay. So this is the value. So this will be ILD for MC. Okay. So this is how you will draw the ILD for different sections when it is subjected to a point load, or sometimes it will happen now later on you will see that you will draw the ILD not for a point load but also for a UDL load. So how you have calculated the values you will see in the coming slides. So now let's move forward and have some thorough idea to the another things also that you have covered. So in this week, you also have covered that what is Muller Breslau principle. So what it say that, so if you want to draw the influence line for any force for response function in a structure, it is given by the deflective shape of the structures resulting from a unit displacement or reaction corresponding to the force or moment under consideration. So the main point is you have to remember here is uh, let me yeah. So it is based upon the deflected shape. Okay. So it is based upon the deflected shape of the member. Yeah. So it is based upon the deflected shape of the structure caused by the unit displacement or rotation. Okay. So what is the main significance here is like suppose you have any beam. Okay. Let me draw a beam. So this is your simply supported beam. If you want to calculate the ILD for a support B, what you will do? First step is you will remove the support from that particular point. Okay. So I have removed the support from point B. Now it is a free point. Okay. The next step is provide a unit displacement to that particular joint wherever you require to calculate the ILD for displacement or rotation. Okay, so let me give this a unit displacement. Okay, so this is your delta AB equal to 1. Now this profile AB will give you the ILD for BY. Okay, this is how you utilize the Muller Breslau principle. So Muller Breslau principle, what it says that in any case you are required to calculate the influence line diagram for either a support a reaction or the moment. So what you need to be do, you remove the particular support from that point, provide a unit displacement or rotation at that particular point, then the deflected shape of the beam will give you the corresponding influence line diagram for that particular reaction. That is, here in this case it is by. Okay, so and this is how you will utilize. But what is the basic concept behind that is the Betty's law. So what Betty's law says that, suppose you have any frame. I think I will crop this and put it in next page. Okay, I will cut this and I will add another slide and I will paste it here. Okay, so what Betty's theorem says that, so suppose you have any frame. Okay, fits at both the ends, subjected to 2 point loads. This is P1 and another point load P2. Okay, and the deflected shape, how it will look like. Since this is a fifth joint, so here slope and deflection will be 0 and it will move like this. And since this is a rigid joint, you also need to know and you need to have to visualize this thing also, that how you need to make the deflected shape. Then you can correspondingly uh, understand the concept in a good and better way. So this is the deflected shape. See, I have made the angle equal to the 90 degree, and now it has shifted to some other location. Here also the deflection is 90, and see the angle between them is between the rigid joint is 90 degree. So this is the deflective shape of the beam due to the load that are acting over it. So let's say this is your delta P1, PQ1. Okay, so we will take now another system, same like this. So suppose we have another frame. Okay, it is also now this frame has a point load at a point where the deflection is delta P1. Okay, I will move this line a little bit above so that it, yeah, now it is fine. So here the load is now acting. mm, yes. So here this Q1 load is acting, and due to that the shape of the profile is like this. Okay. So what Betty's law says that due to these external forces that are applied in the member, see, due to this P1 and P2, the deflected shape here in another frame, that is system 2. So this is your delta QP1, this is your delta QP2. Let's make it as This is your system 1. So this is your system 1, and this is your system 2. So what Betty law says that the force in system 1 into the displacement in system 2 is equal to the force in system 2 multiplied by the displacement in system 1. Okay. So by this, what you will get? You will get it as P1 into delta P1 into delta QP1 plus P2 into delta QP2, that would be equal to Q1 into delta PQ1. Okay. So this is what you will get here. So this is what Betty's law says that. And the same concept is applied in Muller Breslau principle also. Okay. So suppose you have a beam. Okay. See, you have a beam. It has three reactions. This is your AY. This is your BY. This is your CY. Okay. And this is your deflected shape. Okay. And suppose there is one point load here in between A and B right now. And if you make another profile also, see. So now if you apply a certain displacement at point A, and you need to calculate. So let me draw it first. This is your BY1, this is your CY2, this is your BY2, this is your CY2. Okay. Now you need to calculate what will be the uh, reaction at point A when it is subjected to this kind of deformation. So in this, apply a certain amount of displacement to point A. You will see the deflected shape of the profile looks like this. It is moving here from to 0, and then it will move like this. Now the corresponding displacement of point A will give you this delta H. So this is your delta H corresponding to the unit load, and this is your uh, delta A corresponding to the reaction force. Okay, so now apply Betty theorem. What you will get? So if you apply Betty's theorem, so it is summation of forces in system 1 multiplied by the displacement in system 2 is equal to the summation of forces in system 2 multiplied by the displacement in system 1. Okay. So in system 1, the for one force is two forces are acting. One is AY and another is point load 1 kilonewton. Okay, so if you take AY, so AY into delta A, that will be equal to no, plus 1 kilonewton also. uh, No, I will add negative here because the deflection is upward, but the load applied is downward. Whereas in case of AY, the deflection is also upward and the AY is also applied in upward direction. Okay, so this is your delta H. We can add BY, CY also, but it will be multiplied by 0 in system 2. So there is no point of adding that. So what will be the force in displacement 2? So the only force in displacement 2 is FA, corresponding to which the displacement is 0. So that means there is no force, the value is 0 in right hand side. So what you will get? You will get AY equal to delta H upon delta A. This is what Betty's law says that. So if you keep the delta A equal to 1, your AY will be equal to delta H. So that is why we apply a unit displacement at that particular point to determine the corresponding value of deflection due to the moving load that is provided over the certain length of the beam. So the torus so influence line diagram of AY is the deflected profile beam corresponding to delta H equal to 1. This is what Muller-Breslau principle says that. Okay, so there are also another significance of this Muller-Breslau principle. So what it says that it is also used to study the effect of moving load on a structure. Another is it is also used to find out the maximum value of stress function due to the live load. So suppose a train is moving, you need to calculate what is the stress at that particular section or a critical section on the member. So how you will do? You will draw the influence line diagram, and wherever the value is maximum, you try to calculate the stress at that particular point. And if that stress is within your means yield limit or critical limit or cracking limit, then the structure is considered to be safe. Otherwise, the structure is considered to be unsafe, and we will have to redesign it. Another is that point is telling you the same thing, that finding out any stress function under critical load condition. Critical load condition will help us to determine whether the structure is safe or not. Okay, and this principle is applicable to both determinate as well as the indeterminate structure. So finally concluding that, so your influence line diagram for any force is the deflected shape. So it is the deflected shape corresponding to unit rotation or displacement provided at a particular joint or a member under consideration. So what is the purpose for that? It will help us to calculate the effect of moving loads on the structure. It will help us to determine the maximum value of stress in that particular member, and also it will help us to check whether it is within the uh, critical limit or not. Okay, otherwise we have to again redesign that member. So it is based upon Betty's law, which tells us that the force summation of force in system 1 multiplied by the displacement in the system 2 is equal to the summation of forces in system 2 multiplied by the displacement in system 1. Okay, so now let's have some idea about the questions you have to solve based upon this influence line diagram. So first question is uh, the ordinate of the influence line at a particular point C. So you need to calculate the ordinate value at point C while finding out the influence slide diagram for the reaction of support B. So it means you have to determine the value of ordinate at point C when you are drawing the influence line diagram for support B. So what we will do? So to find out the influence line diagram for support B, okay, first remove support from B. Then you have to apply upward force to find the deflected shape of the beam. Okay, when the displacement at B is 1. Okay, so make it so I will copy the same diagram. Okay, you make it in there. So if I remove this member and apply a unit deflection, so if this is my unit deflection, okay, so now the at point B there cannot be any deflection, and it will continue same till point C. Okay, then at point C, since it is hinge joint, it will move like this, and this is your final ILD when a unit load is applied at or unit displacement is provided to support B. This is your ILD for BY. Okay, so in this case, what is the problem? I think I should remove this because it's looking tilted. I will draw it again. Yeah, this looks good. Yeah, no, it's fine. Okay, so in this case, now let's find out the ordinate for the point C. Okay, so use it like suppose this is your H. Use concept of equal triangles and this value is 1. So your H upon C will be equal to 1 upon 10. Okay, so your H will be equal to 3 by 10. So due to a unit displacement at point B, your deflection at point C is coming out to be point 3. So the ordinate value at C will be equal to 3 by 10. Okay. This is how you need to calculate the value of ordinate at any particular point when it's subjected to a uh, unit displacement, or when you have to calculate what is given. It is given you have to find out the influence line diagram for the reaction at support B. So if you are drawing the influence line diagram for support B and you are required to calculate the influence ordinate value at point C, so this is how you will do that. Another question is that you have a simply supported bar of length 25-meter subjected to a uniformly distributed load of 10 kilonewton meter, and this load is greater than the span, and it is moving from right to left of the beam, and you have to calculate the maximum absolute value of the bending moment at a point 5 meter from the left hand support. Okay. So in this case, we will keep the whole load over the span, because if we keep whole load over the span, then only we will be able to determine the maximum bending moment. Okay, so first draw the beam. So suppose this is our bending, our beam of length 25 meter, and it is subjected to uniformly distributed load over the whole, I think more than over the span. So what we will do, we will utilize it whole over the span, and we will take the extra part over more than that. Okay, so this is your UDL of 10 kilonewton meter. Okay, so now if we have to draw the bending moment diagram for this profile, what we have to do, we have to take a unit load at the center, or not at the center, because it is given a point, unit load, it is at a distance of point 5 meter from the left hand support. Okay, so if we draw, yeah, let me again see why it is not right. So if I draw the bending moment corresponding to x equal to 5 meter, so what will happen, so it will be like this. So this is 5 meter. Okay, yeah. So what is this value? This value will be equal to 1 into 5 into 20 divided by 25, and this value will be equal to 4. Okay, so the maximum ordinate value when it is subjected to uh, influence unit load at at a particular distance of 5 meter from the left hand support, its value comes out to be 4. Okay, so now you are required to calculate the bending moment at that point C. So so how you will calculate, uh, so bending moment diagram at point C will be equal to the area of this. So it will be 1 by 2 into 4 into 5, uh, 1 by 2 into 4 into what is the whole length, that is 25. So now you get the whole area under this, and what will be the corresponding distance. So corresponding distance will be, corresponding load is 10 kilonewton per meter. So this is your area under the bending moment diagram subjected to unit load when at a distance of at a distance of 5 meter from the support. So multiplied by the given load, that is 10, you will be able to calculate the bending moment at point C, and it will come out to be 100 into, this will be 100 into 10,000, 1000 by 2, it is comes out to be 500 kilonewton meter. Okay, this is how you are required to calculate the bending moment at any point when it is subjected to point load more than the length of the span. Okay, now let's move to another question. So now, if the same thing, uh, yeah, I think in the previous question also only, the absolute maximum shear force at a point 10 meter from the right hand support. So when it is at a distance of 10 meter from a right hand support, so what is the journal formula we have seen? We have seen the VC will be equal to H upon L, and then other it will be equal to 1 minus H, or L minus H upon L. I will write it again. It, so now if we are considering right hand side will be plus, if I consider left hand side it will be minus. So if I draw the in ILD for that member, for it will be H upon L. So this is positive, this will be negative. Yeah, so this value will be H is 10 here, so it is 10 upon 25, and here H is 25 minus 10 upon 25. In minus sign it is 15 upon 25, it will be 3 by 5, and it will be 2 by 5. Okay, this is how we are needed to calculate the shear force at any particular point. Now we are required to calculate maximum shear force at point D. So how we will calculate? We will take the area in which the maximum area. So the maximum area comes out to be this dude at this point, because the length is also maximum and the value is also, here the value is zero point 0.6, here the value is zero point 0.4. Okay, so this part is maximum, because if we consider the whole area, so both of them will counteract each other and we get a lower value compared to what we are expected to get. Okay, so as the length of UDL is more than the beam length, so to get maximum shear force at D, the UDL should be placed over AD. So I will mark it as A, B. This will I mark as D over AD only. Okay. So the absolute maximum shear force at D will be equal to 1 by 2, and the length is 15 and the value is 3 by 5 multiplied by the load. So load is 10. Okay, so what will be the value? This will be 3 3 is 9 to 10, 90. 90 upon 2 is 45. 45 kilonewton we will get as the maximum shear force at point D when it is subjected to, when we are required to calculate the shear force at a point D, which is at a distance of 10 meter from the right hand support. So now let's move to another question, which says that let us uniformly simply supported beam of length which is less than the simply supported beam moving from left hand to right hand side. So to get a bending moment at point A, what will be the position of the load on the beam? So I think you must have done that derivation, or what we will say, the conceptual thing you have must have seen, but I will also show you that how you can calculate for that also. So suppose you have a beam. Yeah. So we will take a simply supported beam AB. Okay. So we will provide a UDL of length less than the beam length. Yeah. So see, this is the UDL which is less than the beam length. So this whole length of the UDL is B. So this is D, and let the whole beam is divided into A and B. So this is your A, this is your B. Now this will be your A1. This will be your B1. Okay. Let this load will be Q kilonewton per meter. Now let this distance be x. Now let's solve this problem. Okay. So let summation of no and so now summation of moment at B will be equal to 0. So you will get Ay into L, okay, minus this is Q. So Q into what is this load? L minus H, L minus H minus D by 2. Okay. So Q into the distance where we are considering to a point load equal to 0. So you will get Ay equal to Q, and D will also come. Q D into L minus H minus D by 2 divided by L. So this is your reaction Ay. Okay. Now consider the means shear at point C. So what will be this? So here you will have a reaction Ay. Let some load is coming out in between, and this load is A1. Okay, that's why we have divided it into A1 and B1. Now you are required to calculate the shear force at point C. So take the shear force and bending moment at point C, and it is at a distance of x, and this whole distance is A. So take moment about point C equal to 0. So what you will get? You will get Ay into A minus Q A1 A2 equal to MC. Okay. So by this you will get Qy into what is A1? A1 will be A minus H. What is A2? Sorry, this is not A2. This is uh, A1 into A1 by 2. So this will be A minus H by 2 equal to MC. So this implies your MC will be equal to, substitute the value of AD, you will get AY, you will get AD into L minus H minus D by 2 into A upon L minus q into a minus h square divided by 2. So this is your moment due to shear at point C. So to find it out, the maximum bending moment at any point C, we have to take the differentiation of moment about x equal to 0. So we will get minus qd a upon L is equal to q a minus h into minus 1 equal to 0. So what you will get? You will get a minus h upon d is equal to a by L. So this implies what is your a minus h? A minus h a1. So a1 upon a will be equal to d upon L. This will also imply is that a1 upon a will be equal to a1 plus a2 divided by a plus b. Okay, so this will give you a1 upon a will be equal to b1 upon b. Okay, so what you can refer from this that the average load on the left is equal to the average load on the right. Okay, so what is the question what is it is asking to get the maximum value of the bending moment. To get the maximum value of bending moment at A, what should be the position of load on the beam? So, so the answer is the point A divides the UDL length in the same ratio as it divides the beam length. Okay, so this is the final truths. Now let's move to another question in which you have to calculate the ILD for the bending moment at the midspan of the given beam. So to calculate the ILD at the midspan, how you will do that? So for that, you need to provide a unit rotation at uh, point what we can say at a distance of 5 meter from C. So let me draw first the ILD for this. So it will be like here it is 1. Uh, I will add some lines so it will be easy for us to draw that. Okay, so I will start from this point. So it will move like this. Here also it will move like this. Yeah. So this is your ILD for this is your ILD for bending moment at C. C is the not C. I will give it another name. It is E. So this if this is your E, So this is your ILD for bending moment at E. Okay, that's what we have to do in this question. So whenever you are required to calculate the ILD for the bending moment, just make sure to provide a unit rotation at that point. Whenever you are required to calculate the bending moment for the reaction support, provide a unit displacement at that particular support. Okay. So next question, what is says that if in a two load system, so that is a two load system of 175 kilonewton where 100 follows 75. So please remember these things also. Sometimes it is confusing that which one follows which. So here 100 is following 75 and it is moving from left to right. So it is like this. Okay. And the distance between the two is 1 meter. Yeah. This is 1 meter distance between the two. So now you have to determine the maximum second bending moment at the midpoint of the beam. Okay. So again, you have to draw the ILD for the beam and how the ILD for the bending moment at the midspan it will look like. It will look like the same that we have already made. Yeah. So now there are two cases how I can put to get maximum second bending moment at point at the midpoint of the beam. Okay. So this is point D, point C, point B, and point B. A. So here the maximum value is we are required to calculate. It will come out to be, so it is at a distance of 5 meter. So it is 5 into 5 divided by 10, 5 by 2. It is 2.5. Okay. So its maximum value is 2.5. So if I keep this 100 at 2.5 and 1 at 75, then I will get the maximum bending moment. So two cases are there. So two cases. We will solve by both the cases. First one, 100 kilonewton at 2.5 ordinate. Okay. So in this case, your bending moment will come out to be 100 kilonewton. Why I'm writing 100 kilonewton? 100 into 2.5 plus 75 into what is the distance? So this is 1 meter. So uh, so this is your 2.5. So 2.5, 2.5. So 2.5 for 5. And so what will be this value? It will come out to be 2. So your x will be 2. Okay. So your this ordinate will be at a distance of 1 meter will be 2. Okay. So this ordinate will be 2. So it will be 7.5 into 2. So what we will get? You will get the value as 400 kilonewton meter. Another case is when your 100, no, let it put in this way. When your 75 kilonewton is at 2.5 ordinate. So in this case, your bending moment will be equal to 100 into 2 plus 7.5, oh, 75, not 7.5, 75 into 2.5. In this case, you will get the value as 387.5 kilonewton meter. So out of them, the maximum bending moment is 400 kilonewton only. Okay. So whenever you have required to calculate the maximum bending moment at any particular point, provide the maximum load at that particular joint, and also consider whether it will affect your section or not, because sometimes it happens if you put the maximum value at that particular point and again it is moving to negative direction. So if it move to negative direction, then it will provide you a negative result. So check before putting the load whether it is good for you to provide the maximum 100 kilonewton at that particular point, or it is good to provide 75 kilonewton. So in for your consideration purpose, so provide, take both the cases, solve for both the cases, and then whichever value is coming out to be maximum, take that value, and that will be your maximum bending moment for the midpoint of the beam. Okay, so now this is the maximum setting moment that we have calculated. So in the next question, what they have asked to calculate the maximum negative, what they have asked us, I will delete this figure. So they have asked us to calculate, uh, here it is my maximum setting moment. Okay, yeah, right. So what they have done, they have told us to calculate the maximum setting moment in first question, and in another question they have told us to calculate the maximum holding moment. Okay, so let me change this first. So it is maximum holding moment. So if you are required to calculate the maximum holding moment, I will not waste time to draw again the ILD. I will take this same figure. So let me take it and take this figure, and I will utilize this for calculating the holding moment. Okay. So in this case, the maximum value of holding moment here will come out to be uh, so 2.5 upon 5 is equal to x upon 5. So this value will be 2.5. This value will also be 2.5. So it is good for me to put 100 kilonewton load over this point. So if I put 100 kilonewton here, and then 75 will also come. Okay. So 75 kilonewton will come at this point. So this is 100. This is 75. So the value here, if we calculate, it will also come out to be 2. Okay. So in this case, we are calculating the holding moment. So that's why I am considering this area, because only this area is providing us the the maximum holding bending moment. So holding bending moment is considered to be negative. That's why we have to consider the negative area region. So maximum holding bending moment, that will be equal to 100 into 2.5 plus 75 into 2. So that will be equal to 250 plus 150 equal to 400 kilonewton meter. if I have used another case, so this is your case one. If I you have used another case, what would have been happened? So for case two, we'll be having 75 kilonewton here and 100 kilonewton here. Okay, so your bending moment in case two will be 75 into 2.5 plus 100 into 2, and that value comes out to be 387.5. So your maximum value is 400 kilonewton meter. So this case you will, so case one you will consider for maximum bending moment at point. So this is your case two. So your maximum hogging moment will come when the load 100 kilonewton is at point D and your both the system is in between D and C. Whereas your maximum sagging moment will come out to be when the load 100 kilonewton is at a point where maximum bending moment is observed, and another load that is 75 kilonewton is just 1 meter ahead at that point, and its maximum value, the total maximum value of the sagging bending moment is also 400 kilonewton meter. Okay, so now a journal question, that how we can determine the bending moment for different cases. So in this question, what you are required to do, what is the correct influence line diagram for bending moment and reaction at various points of the continuous beam. So suppose you are required to determine the bending moment and shear force at different points of the beam, how you will calculate. So for each case, we will see and then try to determine the influence line diagram. Okay. So first case is you have to find the influence line diagram for bending moment at point C. So this is simple, since at hinge bending moment is zero, hence ILD for bending moment at C will be equal to zero. Okay. Now next question is you have to determine the influence line diagram for shear force at point D. So for that, you have to provide a unit displacement at point D and you have to see how it will work. So, so for shear force at point D, so it means it is like this. Half it is positive, half it is negative. Okay. So here, if you provide positive bending positive shear force, it will continue till point C and it will become zero here. Okay. I will erase this and again make it straight. Yeah. Now this thing will continue here because you have to cut the section, and I will make like this. Okay, this, yeah. So this is the shear force diagram. No, this is not the shear force diagram. This is the influence line diagram for the shear force at point D. Okay. Now how you will draw influence line diagram for the reaction force at at D. I think not at C, it is at D. Okay. So how you will draw that? So for that, provide a unit displacement at point A. So if you provide a unit displacement, this point will further move up. So it would be like this. And at point, yeah, it will be like this, and it will continue to move here like this. And then here it will change the sign, yeah, like this, and also like this. So this value is 1, and this is your influence line diagram for vertical reaction at point D. Now, how you will make for vertical reaction at E? Again, same thing. You will provide unit rotation at point E. Okay. Oh, we have to provide unit rotation, unit displacement at point E. So if we provide unit displacement at point E, so here it is 1. So it will move like this, and then it will move to 0, and this 1 will continue till and it will continue like this. Yeah, and it is like this, and here it is like this. Okay, so this is your influence line diagram for vertical reaction at E. Okay, so here also the 1 kilonewton vertical reaction is provided. Okay, this is how you will draw the influence line diagram for various shear force and vertical reaction along the different length of the beam. Okay, so if you have want to calculate the bending moment at any particular point, provide a unit rotation to that point. Whereas if you require to calculate the reaction influence line diagram for reaction at a point, you will provide a unit displacement at that point. For shear also, you will provide a unit shear at that point, and then subsequently you will calculate the value of shear along the different points of the beam, which will give you the influence line diagram for that particular point. Okay, so in this session, what we have covered all the concepts related to influence line diagram and how we can determine the values of shear force and bending moment pertaining to the moving load along the length of the beam, whether it is point load, UDL load, and sometimes it can be non-uniform point loads, and how it is affecting the structure, that can also be determined. So where this will help us, it will help us to determine the maximum stresses that are developed in that particular section due to the moving load, and also it will help us to determine the critical load carrying condition of the section. So summarizing this whole session, how we have started. So we started with the influence line diagram. So we have done that. Whenever you are required to calculate the influence line diagram for any particular point, take a load, move it from either from left to right and right to left along the number of spans that are provided to you, and then calculate the reactions and moment for each span due to whether the load is there at that point or not. And then based upon the type of load, suppose in this case you have L minus H upon L in both the cases. So if you put the value of H equal to 0, it will come out to be 1. If you keep H is equal to L, it comes out to be 0. So then 1 to 0, it will provide you, this is how it will provide you the influence line diagram for BY. Similarly, for CY, the equation is X upon L. So at X is equal to 0, the value is coming out to be 0, and at L, it is coming out to be 1. So this is how you have calculated for a reaction support. So suppose you have internal point which is E. So how you will calculate? Then you will use your sign convention and provide the shear force at that particular point, and then you will calculate the value of influence line diagram for VE, that is a shear at point E, and ME, that is bending moment at a particular point. Then we have taken another example and also try to find out the influence line diagram for a reaction AY and moment at point A, and then and at a intermediate point with at a distance of B from A support, and then we have determined the value of influence line diagram for shear and the bending corresponding bending moment. Then we have described the Muller Breslau principle. What it says that if you provide a unit displacement at any particular point, it will give you the value of not it will give you value. It will give you the unit load will give you the deflected shape of the structure corresponding to unit displacement or rotation provided to the particular member. So, in which theorem it is based? So, it is based upon Betty's theorem. Then we have tried to solve some examples. So, if you have to determine the ordinate value of influence line at point C, when you have a reaction at point B, so you will provide a unit displacement to the point B, and based upon the type of influence line diagram you have observed, you will came to know what will be the ordinate value at point C. Then, if you have UDL spread over the whole span, so in this thing, you will get the maximum bending moment corresponding to point H is equal to 5 meter, and then this is your bending moment diagram. And when you do multiply by the whole load, that is 10 kilonewton, you will get to know the bending moment at point C. This is your bending moment diagram corresponding to maximum shear for the previous torsion. And similarly, we have taken when you have bending moment which is spread for a small distance which is less than the total length of the beam, then how you will calculate the value of shear force and bending moment. And have a maximum bending moment, it is provided that the average load on the left hand side it should be equal to the average load on the right hand side. Or in other words, what we can say that the way the beam is divided into two parts, in the same way the load should be, or in the same ratio the load should be divided so as to obtain the maximum bending moment. So then we have determined the bending moment for different kinds of spans, and based upon the different loadings, we have calculated maximum bending moment and setting moment, and finally we have uh, defined few profiles of shear force and a reaction force bending moment along different support points to calculate its corresponding influence line diagram. So this is what we have covered in this week. And if anyone has any question, they may can ask now, or they can write it on the discussion forum provided by the NPTEL, wherein a team is there which will correspond to the doubts provided by you for anything which is covered in this week or previous week, or any doubt corresponding to the structure analysis course. So if anyone has any doubt, they can ask right now also. So in this week, we have finalize the influence line diagram and the moving load. So next week, what we will see the analysis of statically indeterminate structures. So till now, we have completed the analysis of statically determinate structures. From next week, we will see the analysis of statically indeterminate structures. So your next part of the structure analysis course will start from the coming week. Hope you have understood each and every concept covered till now. regarding the structural determinate structure, and hope you will like this course and we will utilize this in your civil engineering career for further for further process. So by this, I end this session and hope you have liked this session. Uh, Try to solve as many problems as you can. Enjoy your weekend. Have a nice day.